Hello, my name is Mukund Mundhra and my presentation is on the topic Radix sort. It is a part of my COQ presentation, and so let's start with sorting. So what is sorting? Sorting is any process of arranging items systematically, and it has two common. So the first of them is ordering. So what is ordering? Ordering is arranging items in a sequence ordered by some criteria. Now, what can the criteria be? Say we have a set of numbers, integers, and we want to order them. So different types of ordering can be suggested. They can be sorted into the decreasing order, or so what basically we require here is some a sense of comparison between two numbers, so that given any two numbers I can determine which of these would come before in the order and which would come later in the order. So the second method is categorizing. So what is categorizing? It is grouping items with similar properties. So suppose again I have numbers or integers, and in the range of 1 to 100, and I want to categorize them into bins. My idea of categorizing would be whether it is an odd or even number. So I get two categories and each number would belong to either of the categories. So another method of categorizing would be all the numbers that are in the range from 1 to 10, 10 to 20, 20 to 30, and so on. So that is another way I can categorize the numbers that I have. So what we're gonna study Radix sort here, it is actually it uses bucket sort as a starting technique, and then it uses multiple passes of bucket sort to do the final sorting. So it is actually doing ordering, but it also uses some level of categorizing to obtain its results. So now sorting can be done by in general two types of algorithms. One of them is comparison based algorithms. So like we discussed earlier, that for sorting or for ordering we require a comparison between two numbers, so that given any two numbers I can say that which number should come first and which number should come later. So few sorting algorithms that work on this technique are bubble sort. What bubble sort does is that it checks pairwise for all the elements, for all pairs within the given set, and if even any pair I find that the second element should come before it, I swap the elements. So bubble sort is an order n square algorithm. Quick sort. Now, in the case of quick sort, over the set, I choose any random element that acts as my pivot, and I then arrange the elements such that all elements before it are smaller than the chosen element, and all elements that come after it in the array are greater than the chosen element. Now, once we get this, now this means that the current element is at its right position in the sorted sequence, and I can recursively sort the paths that the part it has divided the original array into. That is the array of the elements lesser than it and the array of the elements greater than it in merge sort. So in merge sort, what we're doing is that we break the original sequence of numbers into smaller parts, recursively sort them, and then combine the results. So as array of size n would be broken into two arrays of subarrays of size n by 2 each, and which will be further broken down into arrays of size n by 4 each, till we reach the base case of single element array n. So one important step in merge sort is combining two arrays of the same size. Both of them are individually sorted, but we want that the combined array should also get sorted, but that can be done in linear time. So overall, the complexity of randomized quicksort and merge sort in the worst case is order of n log n, and it can be mathematically proven that it cannot be improved over that. So So now what we're going to discuss today are some non-comparison based algorithms, such as bucket sort, counting sort, and Radix sort. We will discuss them in detail now. But before you get into that, there is one very important parameter that we need to study is table sorting. Why is table sorting? Because this is something very critical to Radix sort, especially least significant is the Radix sort. So an algorithm, a sorting algorithm where the order of elements having the same key is not changed in the final sequence, such an algorithm is called a stable sorting algorithm. So Suppose if we only have integers, this might not have a much greater effect, because suppose the integers are 1, 3, 5, and 3, so the sorted order is going to be 1, 3, 3, 5. So we can't determine uh, if which 3 comes first or which 3 comes later. But in case these are just keys and they have some actual objects that are linked to them, suppose some class objects are that need to be sorted, and we're just and the comparison is used like a compare to function that determines which object comes before the other one. So in that cases, it is important, if it is required in the problem, then we need to ensure that the sorting algorithm is stable and it does not change the order of them unless required. So a few examples of stable sorting algorithms are insertion sort, bubble sort, and merge sort. You can see in sorting algorithms like insertion sort, bubble sort, and merge sort that the swapping of the elements depends on a condition. So that condition is that only if the second element is greater than the first element, then we swap it. If we remove conditions, if we do not include conditions like swap even when they're equal, so we can maintain the order of the elements and maintain it as a stable sort. So some examples of unstable sort are quick sort, heap sort, and selection sort. So in the quick sort algorithm, when we choose a pivot and we rearrange the elements, so the order gets we lose the initial ordering. And similarly in a heap sort, when we take an element and add it to the heap, we lose the ordering quality of the initial set that we had. So that is why the algorithms are unstable sorting algorithms. Now, bucket sort or bin sort is a sorting algorithm that works by distributing the elements of an array into a number of buckets. So this is like what we initially discussed, something like that. I have numbers from say 1 in the range of 1 to 100, and I want to divide them into buckets and the buckets refer to properties like 0 to 20, 20 to 40, and 40 to 60, and so on. So this is what I can do. Suppose so each bucket I'll take an example here. Suppose we conduct an examination and we want to sort the papers that we have received according to the roll numbers. So say there are 300 students in the examination with roll numbers from 1 to 300. Now if you try arranging them like that, it's going to be very difficult for someone to do it. So suppose we try and optimize it a bit further to make it easier for us. Would be we divide the papers into some buckets, so let the buckets be the roll numbers 1 to 50, 50 to 100, 100 to 150, and so on. So my initial attempt when I go through all the papers would be simply sorting into these 6 buckets. So once I have these buckets ready, so I'll have a bucket that contains only papers that are within the roll numbers 1 to 50, and the second bucket contains papers with the roll numbers 51 to 100. So now I have reduced the initial size of my problem and made it a relatively simpler task. So is that each bucket has to be sorted individually. Either we can use a different sorting algorithm, or we can recursively sort by applying the bucket sort algorithm with now smaller bucket sizes. Now you will see that a bucket sort, it is a stable sorting algorithm. Now one type of bucket sort or a slightly different method that will be used in Radix sort is the counting sort algorithm. Suppose we have an array with n keys and the range of values is from minimum to max, is min to max. So what I'll do is I'll make one separate bucket for the entire range of values from minimum to maximum. So that will give me max minus min plus 1 buckets, and for each bucket I'll maintain a linked list of all the elements that fall into that bucket. So in this case, only if 2 elements are equal, they'll fall into the same bucket. So and at the end, I'll have to concatenate all the buckets. However, I'll have to ensure that the order in which elements were put into the buckets is the same order in which they get concatenated. This is a very important step, as this is the step that ensures that our algorithm is a stable algorithm. So this is what we're doing in counting sort, and the Radix sort algorithm will be using multiple passes of counting sort to perform the final sorting task. Now, for once, if we check the running time of this algorithm, would be that for each element in the array, we'll have to go through all the elements to put them in the appropriate buckets. Suppose there are n elements given to us, and so this will be an order n time. We'll be able to assign each element its appropriate bucket. Now to get the final sorted order, we'll have to go through all the buckets, and for each element in each bucket we'll have to append them to the array. So this is, as we discussed, that as I said earlier, that it is important that the order in which the elements are inserted into the bucket should be maintained so that we can have a stable sorting algorithm. So for each element in B, I'll be appending X to the array. So this will give me a time of order n plus n. So for each bucket, we have n buckets and we have n keys. So the overall running time of the algorithm would be order n plus n. So this is an almost linear sorting algorithm, but it also requires a lot of space. Spatial complexity is again order n. So that is one disadvantage of the algorithm. However, we get a much speed up over the running time. Now, Radix sort introduction. Radix is generally to the base in which a number is represented. For example, Radix 2 numbers are binary numbers, and Radix 10 numbers are decimal numbers, Radix 16 numbers are hexadecimal numbers. So for a number with radix k, the digits of the number can range from 0, 1, 2 till k minus 1. So the if we as the name suggests, I'll be sorting these numbers depending on the depending on the radiuses of the numbers. So one very intuitive idea when we think of radix sort is the um, is using the most significant digit radix sort, and it is used to sort the keys in a lexicographic order. So we'll be coming on the lexicographic order a little later, but for once, if we see the example of radix sort, we'll see that in the most significant digit radix sort, suppose we have the numbers 489, 614, 103, 432, and 617. So I take the most significant digit of the numbers, that is the leftmost digit, and I compare them, and the digits are 1, 4, 4, 6, and 7. So using this, I'm able to form a few buckets depending on the starting integer. So I have the first bucket that contains 103, the second bucket contains 432 and 489, the third bucket contains 614 and 617. Note that this is based only on the first digit. Now within each bucket we'll have to sort individually. So 103, since it is a single element, we don't need to sort it further. Among 432 and 489, initially 489 came first, but now because 8 is greater than 3, the ordering is changed to 432 and then 489. And in 614 and 617, the order remains the same because they cannot be distinguished by 1. So now we can see that 432 and 489 have also been sorted. So 103, 432 and 489 are all sorted and in separate buckets. Whereas in the last bucket, we'll sort 614, 617 depending on the last digit. So it requires 3 total passes of the algorithm of bucket sort algorithm to finally give us the result of the to give us the correct sorted order, which is 103, 432, 489, 614, and 617. Now, the radix sort most significant digit algorithm. It is basically a recursively subdividing algorithm, and the algorithm can be explained as follows. So first, take the most significant digit of each key, sort the elements based on that digit, grouping elements with the same digit into one bucket. So we'll have buckets with the same most significant digit. So now what I have to do is, since all the elements have the same most digit, now I'll have to sort within the bucket. I'll have to check the next most significant digit. So recursively sort each bucket starting with the next digit to the right. Now finally, once I have all the buckets sorted, I'll have to concatenate the buckets together in order. So the most important part again here is to ensure that while concatenation, the order within a bucket should be maintained as it is in the final ordering. So now now we have that suppose we want to order, I want to order or have some strings and I want to order them. Now on the first pass of the algorithm, I will see that the 0 and first strings will get sorted. These two strings get sorted into the enter the first bucket. The strings 2, 3, and 4 enter the second bucket, and the strings 5, 6, 5 enters the third bucket, and the string 6 and 7 enter the last bucket. Now out of these we see that the string 5 the string CAB, it is a single element in the bucket did not be sorted further. Now if you go to the first bucket that contains ACE and ADD, what we have to do is after to recursively sort this bucket, we will be comparing the second element, that is C and D. Since C and D can determine the order of the buckets, we actually never need to compare E and D in this. So similarly, for the bucket with starting element B, the second pass would give me that BAD is the first element, where BED and BEE will give me another bucket which needs to be solved, because I still cannot resolve which of these elements should come before. In the last bucket that contains DAB and DAD, I will need one more pass of the algorithm to determine to compare B and D. So what we see here overall is that what it will have to do, it will take the minimum number of passes that are required, or the minimum number of comparisons required to do this, to actually sort these numbers. So in many cases, when we do not need to look at the lowest significant digits, it will simply skip out the numbers, because we know that numbers have already been sorted. Whereas in some cases it is required, but we will still see that a large number of cases are simply eliminated, thus further increasing the running time. So we can say that it is sublinear in the number of characters in the data. Sublinear, as in it will be much even better than a or a linear dependency on the number of characters. No, but there are certain disadvantages in the MSD algorithm. Is that first of all, it requires recursion and too many intermediate files. Since we are first creating buckets and then we are creating more buckets into the buckets, as we go down, we'll see that a very large number of buckets will be created before we actually start solving the problem. So this requires huge memory problem, first of all, because it needs to store so many intermediate files, and we need to access the memory. Secondly, since we need to sort them, we need to access the memory, and that is quite a random access. So the MSD algorithm is cache inefficient, and which may be cause that might increase the running time of the algorithm slightly, but not theoretically. So now, the second time of Radix sort is the least significant digit first sort. Now in this, what we do is we start from the right end of the algorithm, and we start sorting. So the simple algorithm, that is Radix sort, can be done from the rightmost digit, and around each pass of the algorithm we sort it according to the digit I that we have. In each pass we sort it according to the current digit, starting from the rightmost digit. So in every case we are using a stable sort algorithm, and in most cases the bucket sort or the counting sort algorithm is used. So after each sort we get a better array that is slightly more sorted, but it is only at the end of all the passes that we can get the final sorted array. So before we take an example of it, we'll first go through a proof of it, and when we start with that, we'll make this proof by induction on the number of digits that are there in the numbers. So in the base case involves that there are 0 digits. So if there are 0 digits, we can say that there is sorted because there are no numbers. Now the induction hypothesis would be that assume that the lower order digits, the digits that are less than I, are all sorted. Now what we have to prove that while we are sorting through digit I, we should obtain the correct order. Now say that two digits at position I are different. So the new order after sorting will be correct, because the lower order digits are irrelevant, because digit at a greater order differs. So the digit so suppose we want to do an ascending order sort. So for if we have numbers 567 and 467, 67 comparison, the first two digits would say that the numbers are equal, but or if we have 567 and 483, so it would say that 83 part is greater than 67. However, now if I compare 4 and 5, I get say that 5 is bigger, and because the hundreds place is bigger, I don't actually need to look at the original numbers, the numbers after that, because they don't matter now. And now if two digits are same, so I have say 483 and 467, then we can say that the correct order from the previous sorting was maintained, and this is because we said that it was a stable sort. Because bucket sort is a stable sort, we can say that this is maintained. So now we look to an example of this. So suppose we have the set of numbers 453, 256, 548, 326, 173, 78, and so on. So in the first pass of our algorithm, what we'll do is that we'll look at the least significant digit of these. So 3, this will fall into the bucket 753, 256 falls into the bucket with 6, 548 falls into the bucket with 8. One important thing that we have to note here is that both 256 and 326 fall into the same bucket, that is the bucket with bucket of digit 6, but we need to see here that the order is maintained. So since 256 was there in the initial list first, so here also 256 is inserted into the bucket before 326, and so similarly the other buckets fall into the other numbers fall into the other buckets. And after the first pass of the algorithm, this is something that I would have. This is the now what I have to do is, since I'm done with the first pass of the algorithm, I will have to now traverse to this list to obtain the first sorted list. So the first level of sorting that I've done is, now I'll have to go through this list from left to right, and I'll have to ensure that if I reach a bucket that has multiple entries, I'll have to take the order in which the numbers were entered. So I start with 721, then I get 222, 753, and then 173, and then 144. The number 750 should come before 173, even though this order may not seem correct right now, but this property must be maintained over all the passes. So after this, the sequence that we get is 721, 222, 753, 173. Now if we ignore the left two digits and we look at only the smallest digits, that is least significant, we'll find that this array is sorted according to that. Now we look at the second digit from the right, and we start again putting the elements in the buckets, and this time what we need to ensure is, again what we need to ensure is that if two numbers go to the same bucket, then the relative order should be maintained. So after putting the elements in the buckets, this is something that we obtain. Now if we again at this point, if we ignore the leftmost digit or the most significant digit and look at the other pairs only, we'll find that the numbers are sorted. This is because the previous pass and the current pass have sorted all the numbers up to the last two digits. So we have 21, then 22, and then 26. Similarly 44 and 48, 53 and 56, 73, 75, and 78. Now finally we'll generate the next sorted. After the second pass, the list that we have is again starting from the left: 721, 222, 326, then 144, 548, 753, 256, 173, 875, and then 78. So this is the list that we obtain. Now starting with the most significant digit, I'll start sorting these, and they'll fall into the categories as follows: 7 falls into 721, 222 falls into the bucket 2, so on. I will drop them into all the buckets that they have to fall into. Now, and we should note that since 078 contains lesser number of digits than the other one, so I have appended a 0 at the beginning so that the size of all the numbers is the same. And because 78 is the smallest number, it should fall into the first bucket, as you see. So again, now I start passing through from the left. So the final sorted array that I will receive is 78, 144, 173, 222, 256, and so on. So this is, as we see this, after the three passes of the bucket sort, this is the array that I have received, and we can see that this is the sorted array. Now done with the example. Now if we try to analyze the running time of this algorithm, so if we have, suppose we have the radix use this k, so we have a total of k digits ranging from 0 till k minus 1, and that is equal to the number of buckets that we had in the radix sort. So the running time of the algorithm is order n plus k, where small n is the number of numbers that need to be sorted, and k is the radix used, and which is equal to the number of the buckets. So this is the time required for each pass of the algorithm. Now the total number of passes of the algorithm is equal to the number of digits, and so the multiply, since it is being done in a loop, so the total time that is required with the algorithm is order of d into n plus k, where k is the radix, n is the number of numbers and the size of the sequence that needs to be the size of the array that needs to be sorted, and d is the number of digits. So if suppose k is constant because we take a constant radix, then the complexity of the algorithm is now order d into n. So if we compare it with order n log n algorithms, or the algorithms like merge sort or randomized quick sort, we'll see, although this seems to be linear, but a very simple comparison cannot be made between d and log n, because generally the numbers in whatever form they are represented, it often requires, there is always a very close relation between d and log n. So suppose that I have, what I want to claim here is that this the d into n complexity algorithm is faster than n log n algorithm if the numbers are very small size, that is d is very less. So the Radix algorithm is almost a linear time algorithm, or if I have a sufficiently large data set such that log n is less than d. So Radix sort becomes faster than any comparison based sort. So suppose I take an example that I have 10 numbers that are 1,000 digit each numbers. So uh, since n is very small, because there are only 10 numbers, so and the order n log n algorithm will take much less time, where log n would be approximately 1 if I take base 10, whereas the complexity of the Radix sort algorithm would be 1000n, simply because there are 1000 digits in the numbers, even the number of numbers is very small. So what I'll now, well, as the other case, suppose I have only two-digit numbers, but I have say a million two-digit numbers, then what I can do is that if I have a million two-digit numbers, then the complexity of the Radix algorithm would be 2 into n, which is much preferable. Whereas if I compare it to the n log n algorithm, since n is very large, even log n would be very large, and it would require a much greater than time than it require much greater time than in n log n in the Radix sort algorithm. So for small size numbers or a sufficiently large data set, we see that Radix sort is much faster than comparison based sort. So the Radix sort algorithm can be used to compare. We can use it to sort strings and floating point numbers and integers. Now, if we come to floating point numbers can be represented in the form of a into 2 to the power b. This is generally the characteristic and mantissa form in which they are stored in the memory. So one thing that we can say that if all the numbers had the same value of b, so the 2 to the power b part will be the same. So the numbers just need to be sorted by a. So that we don't need to care about the b part, since we know that it is the same, and all the numbers can simply be sorted by a values, which can be done by a simple bucket sort. Now, suppose we have different values of b, it complicates the picture, but what happens is that basically we know that b is more important than a. So even if for two numbers, the a component of one is much greater than the a component of the other, but if the b component of the first number is greater, we can say that the number with the greater b component is greater. So what we do here, we initially sorted by a first using Radix sort, and once we have the sorted array of the numbers, now we'll do a simple bucket sort on them based on b values. So all the numbers that have a greater b will form into a larger bucket, and we know that they'll have a greater value. One important property that is maintained here, that we're using here, is the stable sort property. So because the initial sorting order algorithm is saved for the numbers with same b, uh, we can say that the ordering with respect to A is not disturbed, only we change the ordering with respect to B, which is more important than the ordering with respect to A. So the another application of them would be sorting strings. Now And the radix sort can be used for sorting strings in the lexicographic order, or it is the order in which we have the elements in the dictionary. So the order used by dictionary is, suppose I have the elements, say they are A, B, C, D, E, F, and G, and AB. So if I want to sort them in the lexicographic order, it will be A, B, B, C, D, E, and F. So A comes before AB in the lexicographic order, just as it comes in the dictionary. So the smaller elements come before the larger elements, even though they have the starting index. That's the first. So radix sort can be used for sorting strings in the lexicographic order, the order used by dictionaries, where one string is greater than another if the first on which they differ is greater. Okay, now if I start with the LSB radix sort to sort strings, so it is only useful when the strings are of the same length, because if there are strings of different lengths, if I sort them starting from the right, then it will create problems when I move towards the left of the first string, if a string with larger number of digits than second string, because I do not know, I'll have to do some sort of padding to ensure that the strings are of the same length. Otherwise, sorting them on using the LSB is not efficient, and neither efficient, and it might give the wrong results as desired by the lexicographic order. So also, since the most affecting positions are on the leftmost part of the string, so it may be possible that we may waste a lot of time sorting strings on the right parts, in the right part of the string, which will actually be changed later and will not make any effect to the original sorting order. So suppose we have two strings, one is a very large sequence of A's and the second one is a large sequence of A with one B at the beginning. So the radix sort, lower LSB radix sort algorithm will start sorting from the rightmost A, and it will sort according to all these A's, and it will be wasting a lot of time sorting for all of them until I reach this end, and I finally say that this should be the correct ordering. Whereas if I had used the other version, if I started from the left, in the very beginning I could have stated that no matter what is after the first character, this would always be the correct order. So this saves a lot of time in running time. So the MSB radix sort, the running time is not only linear in the size of input bytes, but it is also linear in the smallest number of characters in the input that need to be examined to determine the correct order. Uh, this is quite similar to the example as we had seen in the beginning, where we had three character strings. So a lot of options could be simply eliminated because they had already been sorted by the first element or the first two characters, and we did not actually need to compare the third one or the second one in that. So the radix sort, the MSB radix sort algorithm is very helpful sorting strings. Now, the radix sort version of quicksort, where instead of partitioning our input data into two piles based on whether each element is less than or greater than a random pivot, we partition the input into 256 piles, one for each initial byte. Then we can sort each pile recursively using the same algorithm. Um, so one more method of MSB radix sort is the in-place MSB radix sort, which can also called binary sorting. It is done by say we have the initial array, and we have the initial array, and I want to place two boundaries. So since I'm starting with the most significant bit, these will be divided into two parts based on whether the starting bit is a 0 or a 1. And what I'll do is that so I'll place two boundaries. The zero's right boundary will be placed at the beginning of the array, and the boundary for one will be placed at the end of the array. So what I can do is now I'll start scanning the first element from the leftmost part of the array. And now if the digit comes out to be 0, I can simply shift the boundary of the 0 one place to the right, and if it comes out to the 1, I'll swap it with the element to the left of the one's boundary. So, and then I can shift the boundary of ones to one place to the left. So what I'll ultimately I'll be moving the zeros and the ones boundary towards the center of the array, and all elements left of the zeros boundary will have the most significant bit as 0, and all elements to the right of the one boundary would have the most significant bit as 1. So we'll continue this till uh, the 0 and then 1 boundary coincide. So we get two bins in which the initial array is divided. That is in the zeroth one with starting with 0 and one starting with 1. Now we can recursively apply the same algorithm within both the bins to sort them. So this is the in place MSB Radix sort or the binary sort algorithm, and it does not require any extra storage. Now we come to performance comparison. So we are actually comparing the performance of in-place MST Radix sort with the Java's inbuilt array.sort function. So the array.sort function, we see that as we had seen earlier, that the Radix sort algorithm is much favorable when we have either the digit size is very less or the number of or the data set is very large. So we see that in these cases it is almost 3 times faster over large arrays or arrays with a very small digit size. So this comes in accordance with what we had earlier. Now we come to the practical application. So in practice, quicksort and other sorting algorithms are more flexible in terms of the types of data that can be used to sort them, such as because Radix sort basically requires the numbers to be sorted. They require them to be integers, whereas in algorithm like quicksort, I can sort class objects based on some comparison function that determines which object should be placed first, and which need not necessarily depend on the it doesn't need to necessarily depend on some integer value that is associated with it. It can be based on some other quality or other parameters associated with an object. Now, Radix sort has a variable and high space requirement for secondary storage, that is for the buckets. For each bucket, we'll be forming a linked list, and that is what we're because we don't know initially according to the data set as to which bucket will contain how many numbers or how many elements should fall into each bucket. So the space requirement is quite variable for this. And one thing that we compared earlier also was that the comparison of login value compared to the d value, that is the number of digits, so which will help us define which is better, whether a quicksort or merge sort algorithm as compared to a Radix sort. Now this also depends on the data set of numbers that we have. So there are quite a few cases where login may be less than d for practical purposes, and which makes quicksort faster. So in a lot of cases we see that login is less than d. So most library functions for sorting use quicksort algorithms. Okay. Now, so the algorithm for Radix sort was developed in 1954 at MIT, and it has been used quite. It was used to as card sorter algorithm, basically the punch cards that we use in machines, and it provided a speed up over the algorithms existing at that time. So it is used in IBM card sorters to sort large set of punch cards. So each there are 12 rows on a punch card around, and there are 13 pockets. So there is one pocket for each row, plus we have one additional pocket for errors and rejected cards. So we examine a single column on a punch card and place it into the selected pocket. Now first we sort these according to the least significant column, and then proceed column by column to the most significant column. We'll be performing, and this will give us the final sorted array of the cards. That is what is required, and the time complexity will be the same as that we have done till now, and that will be order n to d. Now, one possible improvement is the use of parallel computing. The MSG recursive sorting algorithm has a particular application to parallel computing, as each of the bins can be sorted independently. Now, each pin is passed to the next available processor, and a single processor would be used at the start. So we see that initially we'll divide it into multiple number of pins, and each pin can be assigned to different processor. Now while solving each pin recursively, we'll be forming more number of pins, and as in when we form a pin, we'll assign it to the next available processor. So in the beginning only a single processor would be used, but as we reach the second or third pass of the algorithm, almost all the processor would be used. And ideally, sub bins get solved, the processor load would also reduce, and at the till the end when all the processors are empty and we have it all sorted. So in the worst case, all the keys will be identical or nearly identical to each other, with the result that there will be little to no advantage to using parallel computing to sort the keys, because we see that while forming the mains based on various digits, so you find that if the numbers are quite similar, that the starting few digits would be the same. So till a large number of passes of the algorithm, we'll find that the numbers still remain in the same bin and they do not get divided into smaller bins. So the motivation behind the parallel computing is not actually obtained, because the numbers remain in the same bin. So the algorithm gets more efficient by parallel computing if it gets distributed in a good way by the computer. So now we have the algorithm for this code, and we can this is just what we have discussed till now and can be used for reference later. I hope you had a good experience understanding Radix with me.